Why does a trench barely wider than a highway on most maps still make experienced oceanographers choose their words carefully when they talk about it? It lies in the western Pacific, east of the Philippines, in a stretch of open water that almost no one crosses by choice. At its deepest point, a place called the Challenger Deep, the seafloor sits nearly 11 kilometers below the surface. If Mount Everest were lowered into that gap, its summit would still sit more than 2 kilometers underwater, with room to spare above it. Fewer people have traveled to that depth than have walked on the moon, and more people have orbited the Earth in a spacecraft than have ever seen the floor of the Challenger Deep with their own eyes. Part of what unsettles the people who study the trench professionally is simply its scale relative to our ignorance of it. It stretches for more than 2,000 kilometers along the floor of the western Pacific, a crescent-shaped scar longer than the distance from London to Moscow, and yet detailed, high-resolution maps exist for only a fraction of that length. Entire sections remain known only as smudges on a low-resolution sonar chart, features assumed to exist somewhere within a wide margin of error rather than pinpointed with any real confidence. In a century that has mapped the surface of Mars in fine detail from orbit, this stands out as a genuine, uncomfortable gap in our knowledge of our own planet. We do not know how many species survive in the Hadal Zone, the band of ocean below 6,000 meters named for Hades, the Greek word for the underworld. We do not fully understand why some creatures down there grow unusually large, while others shrink until they are barely visible to the naked eye. We do not know, with any real precision, how the trench's seismic activity connects to the earthquakes and tsunamis that periodically strike the coastlines above and around it. The record is incomplete, and where a record is incomplete, careful scientists stop short of certainty, no matter how tempting a confident answer might be to offer instead. There is a particular kind of unease that comes from studying a place using instruments rather than direct observation, an unease familiar to astronomers studying distant planets and, in its own way, just as familiar to the oceanographers working on this one. A sonar image can tell you the general shape of the seafloor without telling you what moves across it. A water sample can tell you what chemicals are present without telling you exactly where they came from or how long they took to arrive. Each tool answers a narrow question well and leaves the wider picture assembled from fragments, some of them decades old, some of them contradicting each other slightly in ways that have never been fully reconciled. Tonight, we follow the evidence, slowly and in order. We begin with the architecture of plate tectonics, the process that carved this scar into the Pacific floor over tens of millions of years and continues to reshape it today, largely unnoticed, beneath ships that cross it without a second thought. From there, we move down through the physics of crushing pressure into the biology of animals built by evolution to tolerate conditions no engineer would willingly choose to work in. We listen to the trench itself, to tremors that rise from deep within the earth and to the quieter, more recent sounds of human presence that have begun to reach even this far down. And we end at the edge of what the science currently allows us to say, which is not the same thing as the edge of what is actually true. This is not a story that resolves into simple comfort, and it was never going to. It resolves, instead, into a place, a real, physical place, on this planet, still mostly unmapped in any fine detail, still mostly unvisited by human eyes, and still, after more than a century of dedicated study, capable of surprising the very scientists who have spent their careers trying to understand it. That is worth sitting with for a moment before we go any further down into it. None of what follows is designed to frighten. It is designed, instead, to be honest about a place that has earned a reputation for unease the slow way, through decades of careful measurement rather than through any single dramatic incident. Every fact ahead has a name and a date attached to it, a specific expedition, a specific researcher, a specific instrument lowered into the water and later recovered. That is the quieter kind of unsettling. Not a monster in the dark, but a whole stretch of our own planet that has simply never finished revealing itself, no matter how carefully anyone has looked so far. Settle in. There is no need to follow every figure closely, or to remember which expedition came before which. The trench will still be there in the morning, exactly as it has been for tens of millions of years, whether or not any of this is retained. To understand why the trench unsettles the people who study it, it helps to start with a single number, because most of what makes this place difficult defies ordinary description. Ocean depth is usually described in meters, but at Haddle depths, meters stop meaning very much to most of us. A more useful unit, oceanographers often argue, is pressure. At the surface, the air above your head presses down with a force of about 1 atmosphere, a weight so constant and so familiar that the human body has never evolved any way of sensing it directly. At the bottom of the Challenger Deep, that pressure has climbed past 1,000 atmospheres. It is the difference between standing under a light rain and standing beneath the full weight of a loaded freight train, balanced entirely on a single square inch of your body. Almost nothing built by human hands can survive that pressure and still function afterward. Submersibles capable of reaching the bottom of the trench are among the most carefully engineered vehicles ever constructed, built from materials chosen specifically for their ability to resist being crushed rather than for speed, comfort, or ease of manufacture. Even now, only a small number of vehicles on Earth are rated to descend that far, and each one represents years of design work devoted almost entirely to a single problem: how to keep a fragile, air-filled compartment intact at the bottom of an incomprehensible weight of water pressing in from every direction at once. Yet life has been down there for millions of years, adapting slowly to conditions that would instantly disable most of the equipment we send to study it. That contrast between our fragile, expensive machines and the trench's patient, ancient biology is where this story properly begins, and it is worth remembering as we go, because it reframes almost everything that follows. The trench is not simply hostile in the way a storm or a fire is hostile, brief and violent. It is a place where hostility, sustained without pause for tens of millions of years, becomes just another condition to slowly adapt to, the way cold becomes ordinary to a creature born beneath the ice. The trench itself did not appear suddenly, and it did not appear out of nowhere. It is the visible, ongoing result of a process that has been running, quietly and without pause, since long before there were eyes anywhere on Earth to notice it. To understand what the Mariana Trench actually is, and why it keeps shifting beneath the people who study it even now, we have to go back to the collision that made it, and the slow, grinding motion that has never once stopped since that collision first began. It helps to hold two timescales in mind at once as we go. One is the almost unimaginably slow rhythm of the geology itself, measured in millions of years, patient beyond any human frame of reference. The other is the much shorter, much more recent timescale of human curiosity about this place, barely a century and a half old, compressed into a handful of expeditions separated by long gaps of silence. Nearly everything that follows sits somewhere between these two clocks, ancient processes described through the lens of a very young, very limited effort to understand them. Imagine standing on the deck of a research vessel somewhere above the trench, with nothing on the horizon in any direction but open Pacific water. Beneath the hull, invisible and unremarkable from the surface, lies a scar in the Earth's crust, nearly 11 kilometers deep, carved by a process that began tens of millions of years before any ship or any human being existed to sail across it. Nothing about the surface gives away what lies beneath. The water looks like ordinary open ocean anywhere else on the planet, and that, in its own way, is part of what makes the trench so easy to underestimate. The story of the Mariana Trench begins not with water, but with two enormous slabs of rock moving toward each other at a speed slower than a fingernail grows. The Pacific Plate, one of the largest and oldest pieces of the Earth's crust, has spent tens of millions of years drifting steadily westward, carrying an entire section of ancient seafloor along with it. crust in this particular region, estimated to be around 180 million years old, among the oldest oceanic crust anywhere on the planet, formed long before the dinosaurs existed, and older still than the supercontinent Pangaea's final breakup. Where it meets the smaller Philippine Sea Plate, it does not stop, and it does not push the smaller plate aside. Instead, it bends downward and slides beneath it, in a process geologists call subduction, disappearing gradually back into the depths of the Earth from which, in a very real sense, it originally came billions of years ago. The trench is the crease left behind by that motion, in much the same way a rug wrinkles where one edge is pushed under another. This is slow, patient geology, measured in only 2 or 3 centimeters a year, a rate of motion so gradual that no human observer, watching for an entire lifetime, would ever see the seafloor visibly move. But slow does not mean gentle, and it does not mean insignificant. As the Pacific Plate descends, it drags the ocean floor down with it, bending the seabed into the deepest gash on the surface of the planet. Over the tens of millions of years this process has been underway. That gash has deepened into the Challenger Deep, a narrow, canyon-like depression at the southern end of the trench that holds the distinction of being the lowest point in any ocean on Earth. The trench's distinctive crescent shape, curving gently along its entire 2,000-kilometer length rather than running in a straight line, is itself a simple consequence of geometry rather than any unusual local force. A rigid plate bending downward into a sphere, the way the Pacific Plate bends into the curved surface of the Earth, will naturally trace an arc rather than a straight edge. In much the same way a flat sheet pressed against the outside of a ball wrinkles into a curved crease rather than a straight one. Subduction zones around the world, wherever they occur, tend to share this same curved geometry for exactly this reason. And the Mariana Trench is simply one of the clearest, best-studied examples of a pattern that repeats wherever plates sink back into the Earth. Not every subduction zone produces a trench this deep, and the reason the Mariana system does comes down to the particular age and temperature of the plates sinking into it. Oceanic crust cools and becomes denser the longer it sits on the surface, and the section of Pacific Plate feeding into the Mariana Trench is among the oldest, coldest oceanic crust anywhere on Earth. Old, cold, dense rock sinks more steeply and more readily than young, warm crust closer to a mid-ocean ridge, and that steep angle of descent is part of why this particular trench reaches such extraordinary depth compared to subduction zones elsewhere in the world, where younger, more buoyant crust tends to subduct at a shallower angle and produce a comparatively modest trench. Oceanographers describing this contrast sometimes compare it to the difference between a heavy stone sinking straight down through water and a lighter piece of wood being dragged reluctantly under at a shallow angle, resisting the whole way. It helps, too, to place the trench within the wider structure of the ocean, since depth alone can be a difficult thing to picture without some kind of scale. Sunlight fades quickly as depth increases, and by around 200 meters, there is no longer enough light left for photosynthesis to sustain plant life of any kind. Between roughly 200 and 1,000 meters lies a dim, twilight region, where some light still penetrates faintly, and below that, down to around 4,000 meters, lies the fully dark abyssal zone that covers most of the world's ocean floor. The Haddle Zone, the band the Mariana Trench occupies almost entirely on its own, begins only around 6,000 meters down, a boundary so extreme that only a small number of trenches on the entire planet reach deep enough to qualify for the name at all. Nearly everything discussed in the chapters ahead takes place within this narrow, unusually deep slice of ocean, a slice that exists nowhere else on Earth in quite the same form or at quite the same scale. The first hint of what lay down there came not from a dedicated research mission, but from a voyage that set out with an entirely different purpose. In 1875, the HMS Challenger, a British naval vessel converted for oceanographic survey, was crossing the Western Pacific as part of a multi-year global expedition, when its crew lowered a weighted rope over the side to measure the depth of the seafloor beneath them. The line ran out far beyond what anyone on board expected, eventually recording a depth of more than 8 kilometers before finally reaching bottom. At the time, there was no reliable way to confirm whether the measurement was accurate, or whether the rope had simply drifted sideways with the current, adding false length to the reading. It would take more than 80 years, and considerably better instruments, to confirm that the crew of the Challenger had stumbled onto the deepest place on the planet without ever fully realizing what they had found. The trench, and the deepest point within it, would eventually carry the ship's name forward into the 20th century. That confirmation came in 1960, when a Swiss-designed submersible called the Trieste carried 2 men, Jacques Picard and Don Walsh, down toward the floor of the Challenger Deep. The descent took nearly 5 hours, moving through total darkness for almost the entire distance, well past the point where any trace of surface light could reach. Partway through the dive, the crew heard a loud crack that turned out to be a fracture in one of the outer acrylic viewing windows, a detail that did nothing to make the remaining hours of the descent feel routine, and one that both men chose not to dwell on until they were safely back on the surface. Near the bottom, Picard later reported seeing what appeared to be a flatfish moving across the sediment, a claim that has never been fully confirmed or repeated by later expeditions, and one that many biologists now regard with polite skepticism, since no fish has since been documented at anything close to that depth. They spent about 20 minutes on the sea floor, observing what they could through the murky water stirred up by their own arrival, before beginning the long, careful ascent, becoming the first human beings to witness, in person, the deepest point in any ocean on the planet. For more than 50 years after that dive, no human being returned, though the trench was not entirely left alone. In 1995, an uncrewed Japanese remotely operated vehicle named Kaiko became the first vehicle since the Trieste to reach the floor of the Challenger Deep, collecting sediment samples and video footage across several successful missions over the following years. Kaiko was lost at sea in 2003, severed from its support cable during a typhoon, an accident that left the trench once again without any active means of direct exploration for several more years, a reminder of how quickly even a successful exploration program can be interrupted by circumstances no engineer can fully control. It was not until 2012 that filmmaker and explorer James Cameron piloted a specially designed solo submersible, built vertically like a torpedo rather than as a traditional sphere, back down to the same depth, spending several hours alone on the bottom, collecting samples and footage, before an unplanned hydraulic failure cut his exploration short and forced an earlier ascent than originally planned. Cameron later described the descent as one of the most isolating experiences of his life, folded into a cylinder barely wide enough to sit in, watching the light fade through the water outside, long before he was even a third of the way down. Cameron's dive, funded largely through his own resources and years of engineering development, produced some of the clearest imagery yet recorded of the trench floor, along with sediment cores and biological samples that researchers would spend years afterward analyzing. A far more thorough set of descents followed in 2019, when the Five Deeps expedition, funded and personally piloted in part by explorer and former naval officer Victor Vescovo, mapped the Challenger Deep with a level of precision no previous survey had achieved. Vescovo's submersible, a vehicle named the Limiting Factor, completed multiple separate dives across different sections of the trench floor rather than a single descent to a single point, allowing researchers to compare readings across a wider area and begin building the first genuinely detailed picture of the trench's true topography, rather than relying on a single depth measurement taken at one location and assumed to represent the whole system. The same expedition went on to become the first to reach the deepest point of all 5 of the world's oceans, using the Mariana dive as both a proof of concept and a baseline against which the other 4 deep ocean descents would later be measured. Ship-based sonar is not the only tool that has contributed to mapping the trench's broader outline. Satellites orbiting far above the Pacific can detect extremely subtle variations in the height of the sea surface itself, tiny bumps and dips only centimeters tall, caused by the gravitational pull of massive features on the seafloor far below, including the trench's own enormous absence of mass compared to the surrounding crust. By combining these satellite gravity measurements with the more detailed but far more limited coverage of ship-based sonar, researchers have been able to sketch a rough outline of the trench's full length and shape, even across stretches that no research vessel has ever sailed directly over. A reminder that some of the most useful data about the deepest place on Earth has, in a strange twist, come from instruments orbiting hundreds of kilometers above it, rather than from anything lowered into the water at all. Confidence in this entire picture of slow, ongoing subduction rests on more than just the shape of the trench itself. Surveys of the surrounding seafloor have detected long, parallel stripes of alternating magnetic orientation frozen into the crust, as it originally formed at a mid-ocean ridge far to the east, a record left behind because the Earth's magnetic field periodically reverses direction over geological time, and newly formed oceanic crust locks in whatever orientation happened to be in effect at the moment it cooled and solidified. Reading these magnetic stripes like the rings of a tree lets researchers estimate the age of the seafloor at almost any point across the Pacific, confirming, independently of any single trench measurement, that the crust, now disappearing beneath the Mariana system, is indeed among the oldest section of the Pacific Plate still in existence. It is this kind of independent, cross-checked evidence, drawn from magnetism rather than depth soundings, that has allowed subduction theory to move from a plausible idea to one of the most thoroughly confirmed frameworks in all of Earth science. The figure quoted for the trench's maximum depth has itself moved slightly with each generation of survey technology, a small but telling illustration of how difficult this measurement has always been to pin down. A 1,951 survey by the British vessel HMS Challenger 2, the ship that lent its predecessor's name to the deep point it measured, recorded a depth of just over 10,900 meters using early echo-sounding equipment. A Soviet survey vessel operating later in the same decade reported a notably deeper figure, a result that stirred debate for years afterward and was eventually treated with some caution, since the equipment and calibration methods of the period left considerable room for measurement error at these extremes. Only with the arrival of modern multibeam sonar, and later with direct pressure readings taken by descending submersibles themselves, did estimates begin to converge on the figure most commonly cited today, just under 11,000 meters, a number still expressed with a margin of uncertainty rather than as an exact, unchanging fact. Those later expeditions revealed something the earlier ones simply could not have shown. The trench floor is not the flat, featureless plane that popular imagination often assumes it to be. It has ridges, narrow terraces, and localized depressions, shaped both by the same tectonic forces that created the trench in the first place and by periodic landslides that continue to reshape sections of the seafloor even now, sometimes within the span of just a few years between one survey and the next. The most recent detailed surveys place the deepest confirmed point at just under 11,000 meters, though the exact figure has shifted slightly with each new measurement campaign, a reminder that even something as seemingly basic as the trench's true maximum depth has taken more than a century of increasingly sophisticated instruments to pin down with real confidence. Much of what is known today about the trench's precise shape comes from a mapping technique called multibeam sonar, in which a ship trails an instrument that sends out a fan of sound pulses rather than a single narrow beam, recording the time each pulse takes to bounce back off the seafloor and return. By combining thousands of these individual soundings, as a ship slowly crosses back and forth over a stretch of ocean, researchers can assemble a continuous three-dimensional picture of the terrain below, far more detailed than the single-point depth readings that early expeditions like the Challenger relied on. Even this method has limits, since resolution decreases with distance, and a sonar pulse fired from the surface toward a target nearly 11 kilometers away simply cannot resolve fine detail the way the same instrument could at a shallower depth. Mapping the trench with real precision has therefore always required getting an instrument closer to the bottom, whether by lowering it partway down on a cable or carrying it aboard a submersible, rather than relying on surface ships alone. Recognition of the trench's ecological and geological significance eventually led, in 2009, to the designation of a large protected area covering most of the trench and its surrounding waters as a United States Marine National Monument, restricting commercial activities such as fishing and mineral extraction across a significant portion of the region. The designation reflected a growing understanding, built up over the preceding decades of exploration, that the trench was not simply an empty geological curiosity but an active, biologically significant habitat worth safeguarding, even though at the time of the designation, most of what lived within its protected boundaries had still never been directly observed by anyone. What makes this geology genuinely unsettling to the scientists who study it is not the depth alone. It is the fact that the process creating that depth has not stopped and shows no meaningful sign of stopping within any time frame that matters to human plans. The Pacific Plate is still descending beneath the Philippine Sea Plate today, at roughly the same slow pace it has followed for tens of millions of years, grinding forward one imperceptible increment at a time. Somewhere beneath the trench, rock that was once ordinary seafloor is being dragged down into the Earth's mantle, heated past the point of recognition, and eventually recycled into new material that may, over an unimaginably long span of geological time, resurface somewhere else on the planet entirely, in a form nothing like the seabed it once was. The trench is not a static scar left behind by some ancient, finished event. It is a place where the Earth's crust is being actively consumed, one slow inch at a time, at this very moment, whether or not anyone above is paying attention to it. That ongoing motion is also the source of something considerably less abstract than deep time. Earthquakes, some of them originating at depths no other kind of geological boundary on the planet can reach. We will return to what that means for the people living near this stretch of the Pacific later in this account. For now, it is enough to understand that the trench was not carved once, long ago, and then left undisturbed to simply sit in the dark. It is still being carved, slowly, invisibly, in exactly the same patient, ongoing way it always has been, and will very likely continue to be for tens of millions of years still to come, long after every instrument we have built to study it has worn out and been replaced many times over. 10 kilometers down, in complete and total darkness, the pressure pressing in from every direction is close to 8 tons per square inch. It is difficult to translate that figure into something the body can genuinely imagine, so oceanographers often reach for a simpler comparison instead. It is roughly equivalent to the weight of 50 jumbo jets, stacked directly on top of a single standing person. At the surface, water molecules move freely enough to flow around your hand without any noticeable resistance at all. At the bottom of the Challenger Deep, that same water is compressed just enough that its density measurably increases, a small but entirely real physical change in one of the most familiar and seemingly unchangeable substances on Earth. Sailors and researchers on ships above the trench have long used a simple, informal demonstration to make this pressure feel real rather than abstract. A polystyrene foam cup, decorated in permanent marker and lowered inside a mesh bag alongside a deep diving instrument, returns to the surface crushed down to a fraction of its original size, the countless tiny air pockets that give the foam its structure squeezed out entirely by the surrounding water. The marker drawing survives, shrunk but intact, on what is left of the cup, a small and strangely personal souvenir of a pressure most people will never otherwise have any direct way of witnessing. It is a small trick, but it captures something the numbers alone often fail to convey, and it has quietly become a tradition on many research cruises that pass anywhere near the trench. This pressure is the central problem of halobiology, and it is the primary reason the trench remains difficult to study even with modern technology. Most complex life relies on structures, cell membranes, folded proteins, gas-filled cavities that are highly sensitive to changes in surrounding pressure. At depths beyond about 1,000 meters, those structures begin to behave in ways that would be catastrophic at the surface. Proteins, which depend on a precise three-dimensional shape to function correctly, can fold incorrectly under extreme pressure, losing the exact geometry that lets them carry out their biological role inside a cell. Cell membranes, built from layers of fatty molecules, stiffen as pressure increases, and a membrane that is too stiff can no longer let nutrients and signals pass through it properly, effectively suffocating the cell from the inside even while it remains physically intact. Deep-sea organisms counter this membrane problem with a strategy biologists call homeoviscous adaptation, quietly adjusting the composition of their own cell membranes to compensate for the surrounding pressure. Fatty acid molecules can be arranged in straight, tightly packed chains or in bent, loosely packed chains, depending on their chemical structure, and the loosely packed arrangement keeps a membrane more fluid under conditions that would otherwise stiffen it into something closer to solid wax. Organisms living at extreme depth are consistently found to carry a higher proportion of these loosely packed fatty acids in their membranes than their shallow water relatives, a chemical adjustment that appears across many unrelated species to be one of the more universal biological answers to the same relentless problem of pressure. Gas-filled cavities, like the swim bladders many shallow water fish rely on to control their buoyancy, become an outright liability rather than an advantage at extreme depth, because gas compresses under pressure in ways that liquid and solid tissue mostly do not. For decades, this raised a genuine and largely unresolved puzzle among biologists studying the deep ocean. If pressure disrupts basic biological machinery at a molecular level, was there some hard physical limit to how deep complex animals could ever survive, no matter how thoroughly they adapted over evolutionary time? In 2014, biochemist Paul Yancey and his colleagues proposed an answer rooted in a class of molecules called piezolites, small organic compounds that fish accumulate in their tissues specifically to counteract the disruptive effects of pressure on their proteins. One piezolite in particular, trimethylamine N-oxide, increases steadily and predictably in fish tissue as depth increases, appearing to stabilize proteins against the crushing effect of the surrounding water, essentially acting as a kind of internal molecular scaffolding that holds a protein's working shape together against forces that would otherwise distort it. The problem, Yancey's team discovered, is that this compound cannot simply increase without limit. Past a certain concentration in the tissue, trimethylamine N-oxide begins to interfere with the very biological processes it is meant to protect, effectively becoming toxic in high enough doses to the same fish that depend on it for survival. Based on the measured rate at which the compound accumulates with increasing depth, the researchers calculated a theoretical limit for fish, somewhere in the range of 8,200 meters, beyond which no fish, however well adapted its lineage, should be able to survive using this particular biochemical strategy. It was, in essence, a prediction made from chemistry alone, a specific depth at which fish should simply stop appearing in the record, not because the environment itself becomes suddenly impossible to reach, but because the underlying biochemistry runs out of workable solutions. That prediction has held up remarkably well against direct field observation in the years since. The deepest fish ever recorded and formally confirmed, a pale, almost translucent species called the Mariana snailfish, has been documented living at depths of around 8,000 meters, sitting right at the edge of the calculated theoretical limit, and no confirmed fish sighting anywhere on Earth has ever been recorded meaningfully deeper than that figure. Below that threshold, the ocean does not become empty of life. It simply stops belonging to fish and starts belonging to something else entirely, built along a very different biological plan from the start, without the same fluid-filled internal cavities that make pressure so uniquely dangerous for vertebrates. This same pressure problem creates a much more practical difficulty for anyone trying to study hadal life up close, rather than simply observing it on camera. An animal collected at the bottom of the trench and hauled to the surface in an ordinary container experiences a drop in pressure of roughly 1,000 atmospheres over the course of an hour or two, a change its body has no evolutionary reason to be prepared for, since nothing in its evolutionary history has ever moved through that range of pressure at anything close to that speed. Many hadal specimens brought up this way arrive at the surface already dead or badly damaged, their tissues disrupted by the very decompression that should, in principle, have simply released them from a hostile environment rather than harmed them further. To work around this, some research teams have developed specialized pressure-retaining traps, sealed chambers that close automatically around a captured specimen at depth and keep it sealed at close to its original pressure throughout the entire ascent, opening only once safely back in a pressurized laboratory setup on the surface ship. Even with this technology, keeping a hadal organism alive and healthy for any extended period of study remains difficult, and much of what researchers know about the biochemistry of these animals still comes from tissue samples rather than long-term observation of living specimens. Engineering has had to solve a version of this same problem, using entirely different materials and entirely different constraints than biology arrived at over millions of years, and the history of that engineering effort includes real, sobering failures alongside its successes. In 2014, an unmanned hybrid submersible named Nereus, built and operated by American researchers and considered one of the most capable deep-diving vehicles of its time, was exploring the floor of the Kermadec Trench, a hadal trench near New Zealand nearly as deep as the Mariana system, when contact with the surface ship was suddenly lost. Debris later recovered floating at the surface confirmed that Nereus had imploded under pressure, its pressure hull failing catastrophically in what would have been a matter of milliseconds. No one was aboard, since Nereus operated without a crew, but the loss was treated within the oceanographic community as a sober reminder of exactly how unforgiving these depths remain, even for a vehicle built by some of the most experienced engineers in the field. Even staying in contact with a vehicle once it has begun its descent presents its own quiet engineering problem, unrelated to pressure directly but shaped by the same forbidding environment. Ordinary radio signals, the kind used for communication almost everywhere else, are absorbed almost immediately by seawater and cannot travel more than a short distance underwater at all. Submersibles operating at hadal depth instead rely on acoustic communication, encoding data as sound pulses that can travel for kilometers through water far more efficiently than radio ever could, though at a small fraction of the data speed available to a radio or satellite link on the surface. A single short text message or a basic status update might take several seconds to transmit reliably across that distance, and sending anything as data-heavy as live video back to the surface from hadal depth remains impractical with current acoustic technology, which is part of why so much of what a hadal expedition ultimately learns is only reviewed properly once the vehicle has fully surfaced and its recorded data can finally be downloaded directly. Pressure is not the only extreme condition hadal organisms and hadal equipment alike must contend with at the same time. Water temperature at the bottom of the Challenger Deep hovers only a few degrees above freezing, cold enough on its own to slow chemical reactions and stiffen materials that would behave quite differently at room temperature. Combined with the crushing pressure described earlier, this means every adaptation, whether biological or mechanical, has to work under two extreme stresses layered on top of each other at once, rather than facing either condition in isolation. Batteries, seals, and lubricants that perform reliably in a pressure chamber at room temperature can behave quite differently once that same chamber is chilled to match actual seafloor conditions, which is why realistic testing protocols for Hadal-rated equipment typically combine both extremes simultaneously rather than testing pressure and cold separately and simply assuming the results will add up in a predictable way. Long before any new component is ever lowered into open ocean, it is tested on the surface inside a hyperbaric chamber, a sealed steel vessel capable of reproducing Hadal pressure, artificially using pumps and valves rather than several kilometers of actual seawater. Engineers place everything from small electronic sensors to full-scale sections of a pressure hull inside these chambers, gradually increasing the internal pressure to levels matching or exceeding the Challenger Deep itself, watching for the earliest signs of stress, leakage, or deformation, long before the same component is ever trusted with an actual descent. This kind of testing is slow, expensive, and unglamorous compared to an actual expedition, but it is also the only way engineers can find a design flaw safely, on the surface, rather than discovering it 11 kilometers down, with no way to intervene once the failure begins. The pressure hull of a submersible built for Hadal depths is typically a nearly perfect sphere, because a sphere distributes external pressure evenly across its entire surface, avoiding the weak points and stress concentrations that a more complex shape would introduce under load. Titanium is a common choice of material, prized for its strength relative to its weight. Though even titanium must be machined and welded with extraordinary precision, because a flaw invisible to the naked eye can become the exact point where the entire hull fails under enough pressure. Viewing ports, the small windows that let a pilot see outside, are among the most carefully engineered components on the entire vehicle. Built from thick acrylic cones shaped specifically so that increasing outside pressure presses the window more tightly into its seat rather than pushing it inward. A solution that took decades of underwater engineering to refine into something reliably safe. Buoyancy presents its own quiet engineering puzzle. A submersible needs enough lightweight material on board to counteract the weight of its own pressure, hull, and equipment, allowing it to float back to the surface once its dive is complete. But ordinary flotation materials, including simple air-filled tanks, would be crushed flat long before reaching Hadal depths. The solution most modern deep submersibles rely on is a material called syntactic foam, made from countless tiny, individually pressure-resistant glass or ceramic microspheres embedded in a resin matrix, each sphere too small and too strong to collapse under even the pressure found at the bottom of the Challenger Deep. It is, in its own way, a rough engineering echo of the pisolite molecules that fish rely on, a structural solution built from many small, individually pressure-tolerant units working together rather than one large structure trying to resist the pressure on its own. What makes an implosion like the one that destroyed Nereus so difficult to guard against completely is the sheer speed at which it happens. Unlike a slow leak, which might give a crew or an operator some warning before conditions become dangerous, a catastrophic failure of a pressure hull at Hadal depth occurs on a timescale far too fast for any onboard system, human or automated, to respond to. The surrounding water, held back by the hull until the moment of failure, rushes into the resulting gap at tremendous speed, compressing the air inside almost instantly and generating a brief, intense shockwave that can damage or destroy debris across the immediate area. Engineers designing Hadal-rated vehicles treat this risk as an absolute, uncrossable line rather than a matter of degree. A pressure hull for these depths either holds completely or it fails catastrophically within a fraction of a second, with essentially no middle ground for a controlled, gradual malfunction. This is part of why human-occupied submersibles capable of reaching the Hadal zone remain so rare, even compared to the broader field of deep-sea research. Most crewed research submersibles in active use around the world, including long-serving vehicles such as the American Alvin, are rated for depths of a few thousand meters, sufficient for the vast majority of deep-sea science, but nowhere near sufficient to reach the Hadal zone at all. Extending that rating down into Hadal territory demands not just a stronger hull, but a wholesale rethinking of nearly every onboard system, from batteries and lighting to the mechanical arms used to collect samples, each of which must be re-engineered to survive conditions that ordinary deep-sea equipment was never designed to encounter. This is one of the quieter reasons the trench continues to intrigue, and in some ways unsettle the scientists who study it. It is not simply the deepest place on Earth in an abstract, statistical sense. It is a place where a specific, mathematically calculable biochemical boundary appears to divide one entire category of animal life from another, almost as cleanly as a line drawn on a map, and where human engineers, working from entirely different first principles, have arrived at solutions that echo biology's own answers to the same relentless problem, sometimes only after losing an expensive vehicle to learn exactly where the margins truly lie. Very few environments on this planet offer that kind of precision, a limit you can predict from chemistry alone and then go looking for in the dark to see whether nature actually agrees with the equation. In the Mariana Trench, so far, it consistently has. There is a particular kind of quiet respect that seems to develop in engineers who spend years working on this problem, one distinct from ordinary professional pride in a difficult job done well, building something that must survive a single, unforgiving threshold, with no tolerance for a partial failure or a gradual warning sign, forces a degree of caution that few other engineering disciplines require in quite the same absolute terms. A bridge can be inspected for early signs of fatigue and repaired before it fails outright. A Haddle pressure hull offers no such margin, no visible crack to catch in advance, no slow deterioration to monitor over a season of use. It either holds, exactly as calculated, or it does not, and that binary reality shapes the entire culture of Haddle engineering around a discipline of double-checking, redundant testing, and stubborn unwillingness to trust an untested assumption, however reasonable that assumption might seem on paper. Below 8,000 meters, past the point where fish give way to smaller, stranger forms of life, the trench does not go quiet, and it does not go empty. It becomes, instead, a place shaped by an entirely different set of biological rules, where survival depends less on speed or size and more on patience, extreme scarcity, and an almost total independence from sunlight. Nothing that grows here has ever seen daylight in any generation of its lineage, and nothing that grows here needs to. Much of what scientists know about this community comes from a deceptively simple piece of equipment called a baited lander, a weighted frame carrying a camera, a light, and a piece of bait, released from a ship at the surface and left to sink, unguided, for several hours before settling gently onto the trench floor. Within minutes of arrival, cameras deployed this way have repeatedly recorded swarms of amphipods converging from apparently empty, featureless sediment, appearing so quickly and in such numbers that researchers have had to reconsider just how many animals are quietly present in areas that look, at a glance, completely barren. The footage, when it is finally recovered days later after the lander releases its ballast and floats back to the surface, has become one of the more reliable windows researchers have into a habitat that otherwise offers almost no visible sign of the life it actually supports. Some landers are equipped with small traps as well, closing automatically after a set period, so that specimens can be brought back to the surface intact for closer study in a laboratory, rather than only observed remotely on camera. The Mariana snailfish, the deepest confirmed fish species on Earth, offers a useful starting point precisely because it defies most casual expectations of what a deep-sea predator ought to look like. It has no scales, a soft, almost gelatinous body, and skin so translucent in places that its internal organs are sometimes faintly visible through it. The near absence of scales is not incidental. Under extreme pressure, calcium carbonate, the mineral many marine skeletal structures are built from, becomes measurably more soluble in seawater, which may help explain why so many Haddle species have reduced, thinned, or entirely abandoned the hard mineralized structures that their shallow water relatives rely on for protection. The snailfish is not slow because it is weak. It is slow because almost nothing at that depth needs to be fast. In an environment with no ambush predators built for speed and no prey capable of outrunning anything to begin with. Sharing that same depth, and in many ways dominating it more thoroughly than any fish, are small crustaceans called amphipods, particularly a species named Hirondelia gigas. These animals gather in scavenging swarms wherever organic material happens to reach the seafloor, sometimes stripping a substantial piece of bait down to almost nothing within a single day. Researchers studying their digestive systems have found something genuinely unusual: enzymes capable of breaking down cellulose, the tough structural material found in wood and plant matter, a capability rarely found in marine animals, and one that may help these amphipods make use of any plant debris that occasionally sinks all the way down from distant coastlines or drifting vegetation carried out to sea by rivers and storms. Some of these amphipods grow to a size that would be entirely unremarkable in shallower coastal waters, but is notably, sometimes strikingly large for their family of crustaceans, a phenomenon researchers call deep-sea gigantism. Curiously, the opposite pattern, deep-sea dwarfism, shows up in other haddle groups at the very same depths, with some species of worms and mollusks growing noticeably smaller than their shallow water relatives rather than larger. Researchers have not settled on a single framework that predicts which direction a given lineage will take, and it remains one of the more genuinely puzzling patterns in hadal biology that scarcity and pressure appear to push different groups of animals in opposite directions rather than toward any single uniform outcome. The exact cause of gigantism specifically remains genuinely debated within the field, though several explanations have been proposed, and none has been ruled out entirely. Colder water can slow metabolism enough to allow slower, more extended growth over a longer lifespan. Reduced predation pressure at extreme depth may lower the evolutionary cost of taking longer to mature, since there is less advantage in staying small and inconspicuous when almost nothing nearby is hunting for you specifically. Higher oxygen solubility in cold water may also support larger body sizes than would otherwise be sustainable in warmer, more oxygen-limited conditions closer to the surface. It is entirely possible, and increasingly considered likely, that several of these factors combine and reinforce one another, rather than any single explanation accounting for the whole pattern on its own. Alongside the amphipods, live organisms that stretch the ordinary definition of an animal, almost past recognition. Xenophyophores are single-celled organisms, technically classified among the protists rather than true animals, that can nonetheless grow to several centimeters across, an extraordinary size for something composed of only a single cell. They construct intricate, delicate shells from sediment and mineral particles gathered directly from the seafloor around them, building structures that can persist long after the organism itself has died. Their exact ecological role in the hadal environment is still being worked out in detail, though some researchers suspect they may function as a kind of scaffolding or habitat structure for smaller organisms, offering shelter and surface area in an otherwise open, largely featureless expanse of sediment stretching in every direction. Smaller still, single-celled foraminifera, distant relatives of the xenophyophores, have been recovered from sediment cores taken at the very bottom of the Challenger Deep. Their tiny, mineralized shells, surviving in numbers that suggest an active, ongoing community rather than a scattering of chance survivors. Reproduction at these depths often looks quite different from the strategies favored by shallow water relatives of the same animals. Rather than producing enormous numbers of small eggs released into open water, many hadal invertebrates instead produce a much smaller number of unusually large, yolk-rich eggs, each one carrying enough stored energy to let the resulting offspring develop through its most vulnerable early stages without needing to feed itself right away, in an environment where food cannot be relied upon to appear on any predictable schedule. This trade-off, fewer offspring in exchange for a much better chance that each one survives long enough to mature, mirrors patterns seen in other extreme, food-scarce environments across the planet, and researchers view it as one of the clearer evolutionary signatures of what it takes to build a viable population in a place where marine snow is the only reliable food source available. Some hadal species appear to lean on partnerships with bacteria to make that scarce food supply stretch even further. Certain amphipods and worms recovered from extreme depth carry populations of bacteria living within or closely alongside their own tissue, in relationships that researchers suspect may help their hosts break down otherwise difficult-to-digest organic material in much the same way that bacteria living in the guts of many surface animals assist with digestion. The details of these hadal partnerships remain far less thoroughly studied than similar relationships in better-known ecosystems, but the pattern fits a broader theme running through hadal biology. In an environment this short on options, working closely with another organism willing to share the burden of survival appears to be a strategy several very different lineages have each converged on independently, over millions of years of adapting to the same fundamental problem. A short distance away from the trench itself, in the shallower back arc basin behind the volcanic Mariana Islands, lies a very different kind of hadal curiosity. A hydrothermal vent site nicknamed the Champagne Vent, where liquid carbon dioxide bubbles directly out of the seafloor in a form rarely observed anywhere else on the planet. The site supports its own dense community of microbial life, thriving entirely on chemical energy rather than sunlight, in a process called chemosynthesis, in which bacteria extract usable energy from dissolved chemicals rising from the seafloor rather than from any form of light. While this particular vent sits outside the deepest part of the trench itself, it illustrates a broader pattern found throughout this stretch of ocean. Wherever the usual rules of a sunlit ecosystem stop applying, life in this region has consistently found some alternative chemical or structural workaround rather than simply disappearing. None of the life in the deepest parts of the trench depends on photosynthesis, because no meaningful light reaches this far down, not even the faint residual glow that persists at more moderate ocean depths. Instead, the entire hadal food web relies almost completely on what oceanographers call marine snow, a slow, continuous rain of organic material, dead plankton, fecal matter, and other biological debris, drifting down from the sunlit layers of ocean many thousands of meters above. It can take weeks for a single particle to complete that fall from the surface to the trench floor. By the time it finally arrives, it has typically been intercepted, picked apart, and consumed many times over by organisms living at every intermediate depth along the way, so what actually reaches the bottom is a thin, unreliable trickle rather than anything resembling a steady or generous supply. Tracing exactly where a hadal animal's energy ultimately comes from is its own delicate piece of scientific detective work, usually carried out through a technique called stable isotope analysis. Different sources of organic carbon, whether from surface plankton, coastal plant matter, or chemosynthetic bacteria living near a vent, carry slightly different ratios of certain naturally occurring isotopes, chemically identical atoms with a slightly different mass, and those ratios are preserved, largely unchanged, as the carbon passes up through a food web from one organism to the next. By carefully measuring these isotope ratios in the tissue of a hadal amphipod or snailfish, researchers can work backward to estimate roughly what fraction of that animal's diet ultimately traces back to marine snow falling from the surface, versus other, rarer local sources, without ever needing to directly observe the animal feeding in its natural habitat. This method has become one of the more reliable tools for confirming that marine snow really is the dominant energy source across most of the hadal zone, filling in a piece of the picture that direct observation alone, limited to the short window of an occasional camera deployment, could never fully establish on its own. This chronic scarcity shapes almost every aspect of life in the trench. Growth is slow, often dramatically slower than in comparable shallow water species. Reproduction is frequently infrequent and carefully timed rather than continuous. Many hadal organisms appear to have unusually long lifespans relative to their small size, a pattern also observed in other food-poor environments on Earth, where investing available energy in longevity and patience tends to pay off better over evolutionary time than investing it in rapid, energy-hungry reproduction. Some researchers studying hadal amphipods and other invertebrates have suggested that certain species may quietly persist for decades, sustained on a diet that would leave almost anything living closer to the surface undernourished within weeks. Estimating how old any individual hadal animal actually is presents its own quiet challenge, since there is no birth certificate or observed life history to consult for a creature no one has ever watched from hatching to death. Researchers studying certain crustaceans have instead turned to small, hard internal structures called statoliths, tiny mineralized granules that some species use to sense orientation, which accumulate in layers over an animal's lifetime in a pattern broadly comparable to the growth rings found in a tree trunk. Counting and measuring these layers under a microscope offers an indirect but genuinely useful way to estimate age in animals that would otherwise offer no obvious external clue at all, and the resulting estimates are part of what has led researchers to suspect that some hadal invertebrates may live considerably longer than their small size would ever suggest at a glance. One recent discovery ties the trench's biology and its pollution problem together in an unusually direct way. In 2020, researchers formally describing a new species of amphipod recovered from several Pacific hadal trenches, including the Mariana system, chose to name it Erythenes plasticus, a deliberate reference to the microscopic plastic fiber they had found lodged inside the very specimen used to define the species in the first place. The name was chosen intentionally, as a quiet, permanent record built into the species' own scientific identity, that even an animal newly introduced to science, one science had never had the chance to study before human plastic pollution existed at all, could not be described for the first time without also describing the contamination already present in its body. Few discoveries capture quite so precisely the trench's peculiar double status, still yielding animals unknown to science after more than a century of searching, and already marked, at the moment of that discovery, by a form of pollution science has only recently learned to detect. Vision itself becomes an increasingly strange proposition at these depths. In the completely lightless hadal zone, eyes offer no advantage in detecting sunlight that will never arrive, and several species collected from extreme depth show reduced eyes, or in some cases no functional eyes at all, a pattern of loss that appears repeatedly across unrelated lineages that have each independently abandoned a sense with nothing left to detect. And yet bioluminescence, the production of light by living organisms through internal chemical reactions, still turns up even at these depths, produced not to see by but to be seen, or occasionally not seen, depending on the purpose. Some hadal and near-hadal organisms are thought to use brief flashes of light for communication or startlement rather than illumination, a light source built for an audience of other animals rather than for the animal's own navigation through the dark. It is a reminder that darkness this complete does not eliminate the usefulness of light entirely. It simply changes, completely, what that light is for. There is also something that Trench's biology has conspicuously not offered. Despite more than 60 years of searching with increasingly sophisticated tools, the giant, monstrous creatures of popular imagination, the sea serpents and leviathans that folklore and speculative fiction have long placed in the ocean's deepest, darkest reaches. What the Trench has produced instead is smaller, stranger, and in its own quiet way considerably more unsettling, precisely because every part of it is real and documented rather than imagined. A translucent fish surviving at the exact mathematical edge of what biochemistry permits. A crustacean grown unusually large in total, permanent darkness, carrying digestive enzymes rarely seen anywhere else in the animal kingdom. A single cell, building an elaborate, persistent shell out of the very seafloor it lives on. These are not monsters built for drama or spectacle. They are the actual, carefully documented result of tens of millions of years spent adapting, patiently and without any observer watching, to conditions almost nothing else on Earth has ever had to face. None of these organisms exist in isolation from one another. Despite how sparse and scattered the trench floor can appear in a single photograph, the scavenging amphipods depend on the same falling marine snow that feeds the snailfish's smaller prey. The xenophyophores, in turn, may offer shelter to organisms too small for any camera to resolve clearly, forming a loose structural foundation for a community otherwise built on open, featureless sediment. Every one of these relationships had to be pieced together slowly, from scattered samples and brief video recordings gathered years apart, rather than observed directly as a single, continuous ecosystem, the way a naturalist might watch a coral reef or a forest. What eventually emerges from that patchwork of evidence is not a simple food chain, but something closer to a whole community, interconnected in ways still only partly understood, quietly persisting in a place built almost entirely out of scarcity. The trench that shakes the world. Beneath all of this quiet, patient biology, the Mariana Trench is also one of the most seismically active places on the entire planet. And this is where the story shifts from strange to genuinely consequential for people living thousands of kilometers away. The same subduction process that carved the trench into existence continues to generate mechanical stress along the boundary where the Pacific Plate slides beneath the Philippine Sea Plate, and that stress does not release smoothly or gradually. It builds quietly for years or decades, and then it breaks suddenly, in the form of an earthquake, releasing in seconds the strain that had been slowly accumulating for far longer than any single human lifetime. What makes subduction zones like this one geologically distinctive is not just the sheer frequency of their earthquakes, but the extraordinary depth at which some of them occur. Most earthquakes happen relatively close to the surface, within the top 20 kilometers of the crust, because that shallow layer of rock is cold and brittle enough to fracture suddenly under stress. But subducting plates carry cold, dense, brittle rock down into the mantle far below that ordinary depth limit, and in doing so, they allow earthquakes to occur at depths that would otherwise be considered physically impossible anywhere else on Earth. Some of the deepest earthquakes ever reliably recorded, occurring several hundred kilometers beneath the surface, have been traced to subduction zones scattered across the western Pacific, including the broader tectonic regions surrounding the Mariana Trench, part of a longer chain of similar subduction systems collectively known as the Izu-Bonin-Mariana Arc, one of the most consistently active seismic belts anywhere on the planet. Seismologists studying this region have also documented something called a double seismic zone, a pattern in which earthquakes cluster not along one single sloping fault plane within the descending plate, but along two roughly parallel planes separated by a gap of several kilometers. The upper plane is generally attributed to the outer, colder crust of the subducting plate, fracturing under bending stress, while the lower plane appears linked to processes happening deeper within the plate's mantle portion, though the precise mechanism connecting the two remains an active subject of debate. Very few subduction zones anywhere in the world display this double-plane pattern clearly enough to study in real detail, and the Izu-Bonin-Mariana system is considered one of the clearest natural laboratories for it currently available to researchers, drawing seismologists from around the world specifically because of how well-defined the pattern is here compared to almost anywhere else. Exactly why rock can fracture at those extraordinary depths in the first place remains a genuinely active and unresolved area of research within seismology more broadly. At several hundred kilometers down, both pressure and temperature are high enough that rock should, according to standard models, behave more like a slowly deforming solid than something capable of snapping suddenly the way shallow, cold rock does near the surface. The leading explanation among several competing theories involves a mineral called olivine, common throughout the Earth's mantle, which can persist in an unstable, metastable form within the cold core of a rapidly subducting plate long after it should have transformed into a denser mineral structure under the surrounding pressure. When that delayed transformation finally occurs, it happens abruptly, releasing energy in a way that can trigger a rapid, localized failure resembling an ordinary shallow earthquake, even at depths where rock is not normally expected to break this way at all. No single explanation has been universally accepted by the field, and deep focus earthquakes remain, even today, one of the more genuinely unresolved puzzles in modern seismology, one that this particular trench has repeatedly offered new data points toward answering. Shallower earthquakes along the same subduction zone carry a more immediate and considerably better understood danger: tsunamis. When the boundary between the two plates ruptures suddenly, displacing a large section of the overlying seafloor upward or downward in a matter of seconds, it can push an enormous volume of ocean water upward as well, generating waves capable of crossing entire ocean basins before losing significant energy. The Mariana subduction zone lies within the broader system of faults ringing the Pacific Ocean, sometimes informally called the Ring of Fire, a system that has produced some of the most destructive tsunamis in recorded human history. The trench itself has not historically been the source of the very largest of these events, but it sits firmly within the same interconnected tectonic system that produces them, a quiet reminder that the forces shaping the deepest point on Earth are the very same forces capable of devastating coastlines thousands of kilometers away, with very little advance warning under the wrong circumstances. In response to that risk, agencies across the Pacific region have deployed networks of specialized ocean buoys, part of a system generally known as the Deep Ocean Assessment and Reporting of Tsunamis Program, capable of detecting the subtle pressure changes on the seafloor that indicate a tsunami wave passing overhead, long before that wave becomes visible or dangerous near any coastline. These buoys relay their readings by satellite within minutes, giving coastal communities a narrow but genuinely useful window to evacuate before a wave generated by a distant subduction earthquake finally arrives. The system exists precisely because the alternative, relying only on how a wave feels or looks once it is already close to shore, has proven fatally inadequate in past disasters throughout the region's history. The practical stakes of understanding this system well extend far beyond scientific curiosity. Engineers and planners across the Pacific Rim rely on seismic hazard assessments, built in part from data gathered at subduction zones like this one, to help set building codes, insurance requirements, and coastal development guidelines for communities that may never have heard of the Mariana Trench specifically, but live within the same broader tectonic system it belongs to. A more complete understanding of how deep, poorly monitored subduction zones behave, gained partly through studying this particular trench, feeds indirectly into decisions made thousands of kilometers away about how tall a seawall should be, or how strictly a new hospital's foundation should be reinforced against future shaking. In that sense, the trench's seismic behavior is never purely an academic question confined to a remote stretch of open ocean, even though almost none of the people whose safety ultimately depends on that research will ever have reason to think about the trench itself. Monitoring the deeper activity itself, at the depths where much of it actually originates, is considerably harder than monitoring the shallower risk of tsunamis near the coast. Ocean bottom seismometers, specialized instruments designed to record ground motion directly on the seafloor itself, have been deployed near subduction zones including the Mariana system, but they remain expensive to place, genuinely difficult to retrieve once deployed, and limited in overall number compared to the dense, well-funded networks of seismometers that blanket populated regions on land. As a result, scientists studying the deep seismicity of the trench are frequently working with a sparser, less complete data set than they would prefer, piecing together what actually happened from a relatively small handful of instruments spread across an area of ocean floor covering many thousands of square kilometers. Not all of the stress along a subduction zone releases as a sudden, sharp earthquake at all. Over the past 2 decades, seismologists working on subduction zones around the world have identified a separate phenomenon called a slow slip event, sometimes described informally as a silent earthquake, in which a section of the fault releases its built-up strain gradually, over days or even weeks, producing almost no shaking that a person standing nearby would ever notice, yet still shifting the seafloor by a measurable amount over that extended period. These events were only detectable once continuous, high-precision monitoring equipment became widely available, and their relationship to the more sudden, damaging earthquakes that occur along the same faults is still not fully understood. Some researchers suspect that a slow slip event might act as a kind of pressure valve, quietly releasing stress that would otherwise contribute to a larger rupture, while others suspect the opposite, that a slow slip event might load additional stress onto a neighboring section of the fault and make a subsequent large earthquake more likely rather than less. Subduction zones in the Izuban and Mariana system have been monitored for this kind of activity only relatively recently, and any conclusions drawn so far remain provisional, awaiting the kind of long-term, continuous seafloor monitoring that has still only reached a small fraction of the trench's full length. There is a further, more recently understood complication layered on top of all this. Some researchers studying subduction zones around the world have proposed that seismic activity along faults like this one may play a meaningful role in the deep carbon cycle, the extraordinarily slow movement of carbon between the Earth's surface and its deep interior over vast stretches of geological time. As seawater and carbon-bearing minerals are dragged down along with the subducting plate, earthquakes occurring along that boundary may create temporary pathways that allow some of that material to be released back toward the surface through volcanic activity, or alternatively, carried even deeper into the mantle than it would otherwise travel on its own. If this proves correct through further study, the trench is not simply a passive site where earthquakes happen to occur. It may be an active, ongoing participant in one of the slowest and least visible chemical cycles on the entire planet, one that helps regulate the very composition of Earth's atmosphere over timescales stretching across millions of years. The wider Izubonin-Mariana arc has a long recorded history of seismic and volcanic activity, stretching back through centuries of observation from the islands and coastlines nearby, a history seismologists use as an essential reference point when trying to estimate how often the largest events along this boundary tend to recur. Because written and instrumental records only stretch back so far, and because a subduction zone can accumulate stress for many decades or even centuries between its largest ruptures, researchers studying this region often have to combine historical accounts with geological evidence, such as layers of disturbed sediment linked to past tsunamis, to build a longer, more complete picture than direct observation alone could ever provide. Even with these combined sources, estimating the true long-term recurrence pattern for the largest possible earthquakes along this stretch of the Pacific remains an inexact science, constrained by how comparatively short the detailed observational record is next to the scale of geological time the fault itself operates on. Deep focus earthquakes carry one further oddity that has puzzled seismologists for decades. Shallow earthquakes are almost always followed by a cluster of aftershocks, smaller tremors that continue for days or weeks afterward as the surrounding rock settles into its new configuration. Earthquakes originating several hundred kilometers down, including many linked to the Izuban and Mariana system, tend to produce noticeably fewer aftershocks than shallow earthquakes of comparable size, sometimes almost none at all. Since aftershocks are generally thought to result from the same kind of brittle fracturing that produces the main earthquake itself, this scarcity raises an uncomfortable question for the leading theories about how deep earthquakes happen in the first place. Since a mechanism based on a sudden mineral phase transition does not obviously explain why that same process would fail to trigger the smaller, secondary ruptures so reliably seen at shallower depths. It remains one of several details about deep focus seismicity that any eventual, fully settled explanation will need to account for convincingly. One promising recent development may eventually ease the shortage of seafloor instruments in this region without requiring a single additional purpose-built sensor. The Pacific Ocean floor is already threaded with thousands of kilometers of fiber-optic telecommunications cable, laid over past decades to carry internet and telephone traffic between continents, largely unrelated to any scientific purpose. Researchers have recently demonstrated that tiny fluctuations in the light signals passing through these existing cables can reveal faint vibrations in the surrounding seafloor, effectively turning an ordinary communications cable into an incidental, continuous seismic sensor stretching across enormous distances without the cost or logistical difficulty of deploying and maintaining a dedicated instrument. This technique remains in relatively early stages of development, near deep subduction zones specifically, but it offers a rare instance in hadal science where existing infrastructure, built for an entirely different purpose, might eventually help close a monitoring gap that dedicated scientific instruments alone have struggled to fill for decades. Data gathered from the handful of ocean bottom seismometers deployed near the Mariana system does not stay purely local in its usefulness. Seismologists studying subduction zones worldwide feed observations from well-instrumented regions like this one into broader global models used to estimate tsunami risk and earthquake behavior at subduction zones that have been studied far less thoroughly, or that lie closer to densely populated coastlines where the stakes of getting the model wrong are especially high. In that sense, every additional seismometer successfully deployed and recovered near the Mariana Trench contributes not only to understanding this one specific stretch of ocean floor, but to a broader, shared scientific effort to understand how subduction zones behave as a general category of hazard, wherever on Earth they happen to occur. None of this seismic activity is visible from the surface in any ordinary, everyday sense. Cargo ships crossing the western Pacific pass directly over the trench, without any indication whatsoever of the forces quietly at work thousands of meters beneath their hulls. But the instruments, sparse as they are, tell a consistent and sobering story. This is not a quiet, dormant crease in the ocean floor, safely finished with its geological work long ago. It is one of the most actively shaking boundaries on the planet, still shifting, still generating deep, unexplained tremors, and still, in ways researchers are only beginning to properly map, connected to processes that shape the wider Earth far beyond the narrow boundaries of the trench itself. There is a particular discomfort in studying a system this active, while knowing how incomplete the instrumentation covering it remains. A seismologist working on a well-monitored fault on land can often point to a dense grid of instruments recording every subtle shift in real time, building a detailed, continuously updated picture of exactly how that fault behaves. A seismologist working on the Mariana system is, by comparison, reading a story with most of its pages missing, inferring the shape of the whole from a handful of surviving fragments, and trusting that the pattern holds steady across the gaps. That is not a comfortable position for a scientist trained to value complete, careful data, and it is one of the quieter reasons this particular stretch of ocean floor continues to demand more attention than its remote, unpopulated surface would ever suggest it deserves. For most of the 20th century, the Mariana Trench's extreme depth was widely assumed to offer a kind of natural protection, a place so remote and so physically difficult to reach that ordinary human activity simply could not touch it in any meaningful way. That comfortable assumption has not held up well against the evidence collected over the last 2 decades, and the discoveries that have overturned it are among the more quietly unsettling findings to come out of hadal research in recent years. In 2017, a team of researchers led by ecotoxicologist Alan Jamieson analyzed amphipods collected from the Mariana Trench and several other hadal locations scattered across the Pacific. What they found in the tissue of these small deep-sea crustaceans was extraordinarily high levels of persistent organic pollutants, including polychlorinated biphenyls, industrial chemicals commonly known as PCBs that were banned from most uses decades earlier, specifically because of their toxicity and their tendency to persist in the environment for generations without breaking down. The concentrations measured in some Mariana Trench amphipods were comparable to, and in certain samples actually higher than, those found in crabs collected from some of the most heavily polluted coastal waterways anywhere on the planet. A result the research team themselves described as unexpected given the trench's extreme distance from any industrial source. A separate line of research has traced an even more specific fingerprint of human activity into the same tissue samples. Studies analyzing amphipods from several Hadal trenches, including the Mariana system, have detected measurable traces of carbon, 1,4 produced by atmospheric nuclear weapons testing carried out in the mid-20th century, decades before most of these organisms were ever collected. That radioactive carbon entered the atmosphere during those tests, was absorbed into surface ocean water and the organisms living in it, and has since traveled downward through the same slow chain of marine snow that carries pollutants and nutrients alike, eventually turning up in the tissue of animals living at the bottom of the deepest trench on the planet. It is a strange kind of confirmation, written directly into the biochemistry of a scavenging crustacean, that no era of human activity, however brief or however distant in time, has stayed fully contained to the surface world that produced it. This was a genuinely difficult result to reconcile with the trench's long-standing reputation as one of the most isolated, untouched environments on Earth. The explanation researchers have proposed centers on the same slow, patient rain of marine snow that feeds the trench's biology in the first place. Pollutants that enter the ocean near the surface, whether from industrial runoff, agricultural chemicals, atmospheric fallout, or the slow degradation of plastic waste, do not simply vanish once they reach the sea. Many of them bind chemically to small organic particles and slowly sink, following the same long, unhurried descent as the natural biological debris that Hadal organisms depend on entirely for food. Over years and decades, that steady descent carries pollution downward just as efficiently as it carries nutrition, gradually concentrating it in organisms living at depths that most people would have confidently assumed were entirely beyond the reach of any surface human activity whatsoever. Plastic debris tells an even more direct and visually striking version of the same underlying story. In 2018, video footage recorded during a submersible dive to the Challenger Deep captured what appeared unmistakably to be a plastic bag resting quietly on the seafloor at a depth of nearly 11,000 meters, the single deepest point in any ocean on Earth. It was not an isolated or one-off incident. A database maintained by Japanese researchers, cataloging thousands of individual sightings of deep-sea debris, recorded by submersibles and remotely operated vehicles over several decades of expeditions across the world's oceans, includes numerous confirmed sightings from Hadal trenches, clear evidence that manufactured waste, drifting and slowly sinking across entire ocean basins, eventually reaches even the single most remote and inaccessible point on the planet's entire surface. Separate studies examining the digestive tracts of amphipods collected from multiple Hadal trenches have found microscopic plastic fibers present in the majority of individuals sampled, a finding that suggests plastic contamination at these depths is not an occasional, isolated event, but a routine and ongoing part of the food supply reaching the deepest parts of the ocean. What makes this particularly troubling to researchers is less the presence of any one plastic bag in isolation, and more what that single, striking image represents about the completeness of human influence across the whole planet. The Mariana Trench sits farther from any coastline and deeper below the ocean's surface than almost anywhere else on Earth. If pollution can reliably reach that far, there is effectively no marine environment left anywhere that can honestly be considered entirely untouched by human activity. a sobering conclusion that carries scientific and ethical weight well beyond the trench itself. This creates a particular difficulty for researchers trying to judge how much any of this pollution has actually changed the trench over time. Because so few samples were ever collected from the Hadal Zone before the mid-20th century, there is very little reliable baseline data describing what pollutant levels looked like in this environment before large-scale industrial activity began. Scientists studying more accessible ecosystems can often compare modern measurements against decades or centuries of historical records, but Hadal researchers are largely working from a starting point that already includes whatever contamination had already arrived by the time anyone thought to look. This problem, sometimes called a shifting baseline, means that even a careful, well-designed study can only describe how much pollution is present now, without ever being fully certain how much cleaner or how different this same environment might have looked 100 years earlier, before anyone had the tools or the reason to check. Sound has proven to be a similarly persistent traveler. Underwater microphones deployed in and around the trench have recorded not only the trench's own natural seismic rumblings, but also the low, steady drone of distant ship engines and propellers, a form of background noise that has measurably increased across the world's oceans over the past century as global shipping traffic has grown. Whether or how this noise affects Hadal organisms, most of which have never been studied for their sensitivity to sound, remains an open question, but researchers increasingly treat it as one more example of surface activity reaching into a place long assumed to be acoustically as well as physically isolated from the rest of the world. There is a second, quieter kind of hiddenness at work here as well, one that has less to do with pollution specifically and more to do with the sheer remaining scale of what has never been closely examined at all. Detailed, high-resolution mapping of the Mariana Trench floor exists for only a small fraction of its total area, despite decades of survey work. Much of what scientists currently know about the broader trench system comes from lower-resolution sonar surveys conducted from ships at the surface, capable of revealing only large-scale features, rather than the finer details that would reveal smaller habitats, localized geological formations, or subtle signs of biological activity below. International efforts, such as Seabed 2030, a collaborative project bringing together governments, research institutions, and private organizations with the stated goal of producing a complete, high-resolution map of the entire global ocean floor, have made real progress in recent years, contributing millions of square kilometers of newly surveyed seafloor to a shared international dataset. But vast stretches of Hadal terrain, including significant portions of the Mariana system itself, remain mapped only in broad, low-detail strokes. Oceanographers frequently point out, almost as a standard line by now, that we possess more detailed maps of the surface of the Moon and Mars than we do of large sections of our own ocean floor, a comparison that has become something close to a cliché in Hadal research, precisely because it remains stubbornly, uncomfortably true. It is a strange kind of asymmetry for a species that has sent cameras to the surface of a comet, yet still cannot say with confidence what covers large stretches of the seafloor within its own planet's largest ocean. Much of the visual evidence supporting these findings exists today only because research institutions have begun systematically archiving decades of submersible and remotely operated vehicle footage that once sat scattered across individual expeditions with little central organization. Japan's National Oceanographic Research Agency, JAMSTEC, maintains one of the largest such archives, a growing library of deep-sea video that researchers can search and review long after the original expedition that captured it has ended, often noticing patterns, like the recurring presence of litter at extreme depth, only in hindsight, by comparing footage gathered years or even decades apart. Without this kind of retrospective review, made possible only once enough footage had accumulated to reveal a pattern, isolated sightings of debris on the seafloor might easily have been dismissed as unusual, one-off occurrences, rather than recognized as part of a consistent, ongoing trend. There is also a quieter methodological challenge running underneath all of this pollution research, one familiar to scientists working in almost any field that depends on rare, expensive sampling. It is one thing to confirm that a pollutant is present once it has been detected in a specimen. It is considerably harder to confirm that a pollutant is genuinely absent from a wider environment based on the small number of samples any single expedition can realistically collect and analyze. A handful of amphipods brought up from one location on one expedition can tell researchers a great deal about what has reached that particular patch of seafloor, but it cannot rule out the possibility that a slightly different pollutant or a higher concentration exists just a few kilometers away in a spot no one has yet sampled. This asymmetry between how confidently a positive result can be reported and how little a negative result can actually rule out shapes how cautiously researchers phrase almost every conclusion published about hadal pollution. And it is part of why so many papers in this field end not with a final answer, but with a call for more sampling across a wider area. Even changes far removed from direct pollution may eventually reach the trench through the same long chain of marine snow that supplies its food. Satellite instruments tracking chlorophyll concentration at the ocean's surface, a rough proxy for how much plankton is growing in a given region, have recorded shifts over recent decades linked to broader changes in ocean temperature and circulation. Because hadal life depends so completely on whatever organic material happens to sink down from those surface plankton communities, any sustained change in how much plankton grows, or in how efficiently it survives, the long, slow fall to the seafloor could eventually alter the food supply reaching the trench floor, even though the connection between a warming surface ocean and a hadal amphipod's dinner has barely begun to be studied directly. It is one more example of how thoroughly this supposedly isolated environment remains threaded into processes unfolding thousands of meters above it and entirely outside its own control. Governing any of this activity across such a remote stretch of ocean is complicated by the fact that large sections of the deep seabed, including parts of the wider region surrounding the Mariana Trench, fall outside the clear jurisdiction of any single nation. International agreements, developed over decades of negotiation under frameworks such as the United Nations Convention on the Law of the Sea, attempt to establish shared rules for activity in these areas, including environmental safeguards, meant to apply even where no single government has direct authority to enforce them unilaterally. Enforcing those shared rules across an area this vast, this remote, and this difficult to physically monitor remains a persistent challenge, one that depends heavily on international cooperation and self-reporting, rather than the kind of direct, continuous oversight available closer to any single country's own coastline. The trench's protected status has not entirely settled the question of future human pressure on this environment either. Elsewhere across the Pacific, growing commercial interest in seabed mineral deposits, valuable metals and rare compounds found in mineral-rich nodules and crusts scattered across parts of the deep ocean floor, has drawn increasing attention to the wider deep sea as a potential resource rather than only a subject of pure research. While the deepest hadal trenches themselves are generally not the primary target of this interest, since their extreme depth makes any extraction effort considerably more difficult and expensive than mining shallower deep-sea deposits elsewhere, researchers studying hadal ecosystems have voiced concern that increased industrial activity anywhere in the surrounding deep ocean could add further disturbance, noise, and sediment plumes to an environment already shown to be far more exposed to surface influence than once assumed. Whether that broader industrial pressure ultimately reaches the trench directly, or simply continues to arrive indirectly through the same slow channels that have already carried plastic, pollutants, and atmospheric fallout to the bottom of the Challenger Deep, remains an open and closely watched question for the scientists who study this region professionally. This combination, pollution reaching farther than almost anyone expected, and detailed mapping falling farther behind than most people casually realize, is part of what keeps the trench genuinely unsettling to the people who study it as a full-time profession. It is not a mystery built on the unknown alone, in some abstract or philosophical sense. It is a mystery built on the measurable gap between how much we habitually assume we understand about our own planet and how little of that comfortable assumption actually holds up once someone goes looking closely enough and carefully enough to check it properly. Isolation, it turns out, was never quite the right word for what the trench actually offered. Distance and depth, clearly, make the trench difficult for people to reach, but difficulty of access is not the same thing as genuine separation from the rest of the planet's chemistry, its debris, or its slow-moving atmospheric history. The trench was always connected by the same patient descent of marine snow that has fed its biology for millions of years to everything happening in the sunlit ocean thousands of meters above it. Pollution simply followed a path that nutrients had already been traveling along for far longer, arriving late, but arriving all the same, exactly the way anything carried by that same slow current eventually would. The questions the trench keeps. After more than 60 years of crude and uncrewed exploration, the Mariana Trench remains, by any honest and careful accounting, one of the least understood environments on the entire planet. This is not a failure of scientific effort or curiosity. It reflects the genuine, ongoing difficulty of studying a place that actively resists close observation at every stage, where every single dive requires enormous financial cost, extraordinarily careful engineering, and a narrow operational window measured in hours, rather than the days or weeks available to researchers working in more accessible environments. One of the most basic open questions is also, frustratingly, one of the hardest to answer with any confidence. How many species actually live in the Haddle Zone at all? Every expedition to the trench in recent decades has returned carrying organisms that did not match any previously cataloged species, a pattern that shows no meaningful sign of slowing down as sampling methods and equipment continue to improve. Some researchers estimate that a substantial portion of Haddle biodiversity remains formally undescribed by science, not because the organisms themselves are especially rare in their own environment, but simply because so few samples have ever been collected from an environment this genuinely difficult and expensive to reach. Each new dive functions less like a routine survey of an already well-known system, and more like a genuine first glimpse into a largely uncatalogued world hiding in plain sight beneath the waves. There is also the open question of connectivity, or the lack of it, between separate Haddle trenches scattered around the world. The Mariana Trench is only one of several such trenches distributed across the Pacific, alongside others including the Kermadec Trench near New Zealand, the Tonga Trench, and the Izu-Ogasawara Trench closer to Japan, each with its own recorded depth close to or exceeding 10,000 meters, and each separated from the others by thousands of kilometers of comparatively shallower ocean that many Haddle organisms may be physically incapable of crossing, given how narrowly and specifically some species appear to be adapted to a particular, extreme range of pressure. Comparative sampling across several of these trenches has already turned up amphipod populations that appear closely related between certain trenches while remaining puzzlingly distinct from others nearby. A pattern that does not yet fit neatly into any single explanation and suggests the true picture of connectivity across the Pacific's Haddle trenches may be considerably more complicated than a simple story of isolated. This raises the genuine possibility that each individual trench may host its own distinct set of species, evolved in relative isolation over millions of years, effectively functioning like isolated islands scattered across the bottom of the ocean, rather than forming one single, continuous, freely connected habitat. Confirming or disproving this idea more fully would require careful comparative sampling across many more trenches simultaneously, an undertaking that remains logistically difficult, extremely expensive, and so far only very partially completed by the international research community. Newer techniques may eventually make that kind of comparison more practical, than it has been. Environmental DNA sampling, a method that detects genetic material shed naturally by organisms into the surrounding water, rather than requiring a physical specimen to be captured and brought to the surface, has begun to be tested in hadal environments, offering the possibility of surveying a much wider area for signs of unfamiliar species without the enormous cost of a full submersible expedition for every single sample. The technique is still young in this particular setting, and researchers remain cautious about over-interpreting results gathered this way, since a genetic trace alone cannot always confirm exactly which species produced it or precisely where within the water column it originated, but it represents one of the more promising paths toward finally closing some of the trench's most basic and persistent knowledge gaps within the coming decades. The trench's underlying geology raises its own set of stubbornly unresolved questions. Researchers still do not have a complete, settled picture of exactly how subduction zone stress accumulates and eventually releases at the extraordinary depths where the largest deep-focus earthquakes originate, nor a fully agreed-upon explanation for what physically allows rock to fracture suddenly at pressures and temperatures that should, according to standard models, prevent that kind of brittle failure entirely. Better, more confident answers would require substantially more seafloor seismometers than currently exist anywhere near the region, instruments that remain genuinely difficult and expensive to deploy and reliably maintain across such a remote and hostile stretch of open ocean. Even the trench's most basic physical dimensions remain subject to periodic revision as technology improves. Each new high-resolution survey conducted over the decades has produced a slightly different figure for the maximum depth of the Challenger Deep, not because the trench itself is changing dramatically between one survey and the next, but because measuring it with real precision through several kilometers of water, using instruments that must carefully account for variations in temperature, salinity, and pressure at every single depth along the way, is a genuinely difficult and unforgiving technical problem. The figure most commonly cited today is considerably more precise than the rougher estimates from decades past, but few working oceanographers would confidently call it the final, unchangeable word on the subject. Part of what keeps all of these questions open longer than researchers would like comes down to a plain, unglamorous constraint. A single Hadal expedition, factoring in ship time, specialized crew, and the construction or maintenance of a Hadal-rated vehicle, can consume a budget many times larger than a typical research grant, covering years of work in a more accessible field. Because that money has to be assembled from a relatively small pool of government agencies, universities, and occasional private philanthropists willing to fund this specific kind of extreme exploration, Hadal expeditions happen on a schedule set largely by fundraising rather than by scientific urgency alone. Every open question described in this chapter, in that sense, is competing not only against the genuine physical difficulty of reaching the trench, but against every other worthy use of the same limited pool of expedition funding, a quieter and less dramatic obstacle than pressure or darkness, but in practice, often the more decisive one. Interest in returning to the trench in person has not faded since the last major expedition. Organizations involved in earlier Hadal descents have continued to announce plans for further crewed dives to the Challenger Deep and to other Hadal trenches around the Pacific, often framed explicitly as opportunities to carry working scientists to the bottom alongside professional pilots, rather than treating each descent primarily as an engineering demonstration or a personal achievement for a single explorer. Whether these plans proceed on the timelines currently proposed depends on the same combination of funding, engineering readiness, and favorable weather that has shaped every previous expedition to this depth. A reminder that even now, more than a century and a half after the first sounding line was lowered, reaching the trench remains an undertaking measured in years of preparation for every single hour eventually spent on the bottom. There is also a broader, largely unanswered question about what role trenches like this one play in the ocean as a whole, beyond serving as an isolated habitat for the organisms living directly within them. Some researchers have proposed that Hadal trenches may act as unusually efficient traps for organic carbon, funneling material down steep slopes into these narrow depressions and burying it in trench sediment at a higher rate than occurs across the flatter abyssal plains that make up most of the deep ocean floor. If that proves broadly true across multiple trenches, Hadal environments may play a small but genuinely significant role in the planet's long-term carbon cycle, quietly locking away organic material for extended periods in a handful of narrow, largely overlooked seafloor depressions scattered around the world's ocean basins. The idea remains under active investigation, and the Mariana Trench, as the deepest and among the most studied of these features, is expected to remain a central test case for it in the years ahead. Some of the interest in finally closing these gaps comes from a field that, on the surface, has nothing to do with the ocean at all. Researchers studying the possibility of life beyond Earth have increasingly looked to hadal trenches and deep hydrothermal systems as the closest available analogs for environments suspected to exist on icy moons elsewhere in the solar system, places such as Europa and Enceladus, where liquid water is thought to exist beneath a thick shell of surface ice, entirely cut off from sunlight in much the same way the Hadal Zone is cut off from it here on Earth. If life can adapt to total darkness, extreme pressure, and chronic food scarcity in the Mariana Trench, relying on chemical energy and patient, low-energy survival strategies rather than sunlight, that offers at least a partial, cautious template for what life elsewhere in the solar system might need to tolerate, and how it might be recognized if a future mission ever finds a trace of it. The trench, in other words, has become useful not only for understanding this planet, but as one of the nearest, most accessible testing grounds we have for imagining what survival might look like on a world we have never visited at all. That connection runs in an unexpectedly practical direction as well. Some of the same pressure-tolerant materials, sealed housings, and low-power sensor designs developed for Hadal submersibles have found their way into the early design considerations for future planetary landers intended for the outer solar system, where extreme cold and, in some proposed missions, extreme pressure beneath an icy shell present engineering problems that echo, in broad outline, exactly what Hadal engineers have already spent decades solving here on Earth. It is a small, quiet irony that a stretch of ocean floor so difficult to reach that most people alive today will never see so much as a photograph of it in detail may end up shaping how humanity eventually tries to look for life on a world millions of kilometers away, simply because both problems, in the end, come down to surviving somewhere sunlight and easy access were never going to reach. There is a kind of scientific humility that working on the trench seems to instill in the people who spend their careers doing it, a humility distinct from simple caution. It comes from repeatedly discovering that a comfortable assumption that the deep ocean was too remote for pollution to reach, that a fish could simply keep adapting to any depth given enough evolutionary time, that the seafloor here was static and finished, did not survive contact with a closer, more careful look. Scientists working in more accessible fields sometimes have the luxury of assuming that most of the basic groundwork has already been done, and that new research mostly refines details around an already solid foundation. Hadal researchers rarely have that luxury. Nearly every expedition still has a real chance of overturning something that had, until that point, seemed reasonably well settled. Taken together, the total record of direct human exploration of the Challenger Deep still fits into a remarkably short list. A small number of crewed descents across more than 60 years, a slightly larger number of uncrewed submersible and remotely operated vehicle missions, and a modest, growing collection of baited landers and sediment cores gathered a little at a time, one careful expedition after another. Compared to almost any other scientific frontier, still actively studied today, from the surface of distant planets to the human genome, the Hadal Zone has been sampled a vanishingly small number of times relative to its sheer physical size. Several national oceanographic institutes and international partnerships have announced plans for more sustained Hadal research programs in the years ahead. aiming to deploy more permanent seafloor monitoring equipment and to carry out more frequent, more systematic biological sampling than the occasional expedition-by-expedition approach that has defined Hadal science so far. Whether that ambition translates into a genuinely comprehensive picture of the trench within the coming decades, or simply into another incremental improvement on an already slow trend, remains, like so much else about this place, an open question rather than a settled outcome. It is worth distinguishing, too, between the kinds of unknowns already described here and a different, harder category that Hadal researchers are far more reluctant to speak about with any confidence at all. Every open question listed so far, an uncertain species count, an unresolved earthquake mechanism, an incomplete pollution map, is at least a known gap, a question researchers can name clearly, even if they cannot yet answer it. There is very likely a second, less visible category of gaps that has not even been identified as a gap yet. Questions no one has thought to ask because nothing collected so far has hinted that the question exists. Every major Hadal discovery of the past 60 years, from deep-sea gigantism to pressure-driven mineral solubility to plastic reaching the deepest trench on the planet, was, at some earlier point, exactly this kind of invisible gap, unnoticed simply because no one had yet gathered the piece of evidence that would reveal it. There is no way to know in advance how many more gaps of that kind remain, waiting for a future expedition, a future instrument, or simply a future researcher looking at old data with a new question in mind. What ties all of these open questions together is not any single dramatic unknown, standing above the rest, but the accumulated, quiet weight of an entire environment that has been visited far less often than it has been theorized and speculated about from a comfortable distance. Every answer the trench has given up so far has arrived slowly, expensively, and quite often accompanied by 2 or 3 brand new questions arriving right alongside it. That is not typically how scientific discovery feels in fields with easier, cheaper access to their subject matter. It is, however, exactly how discovery has always felt in the one place on this entire planet that has never once made itself easy to reach, and shows no particular interest in starting now. The Challenger Deep is still down there tonight, resting in the same quiet dark it has occupied for far longer than there have been eyes anywhere to notice it. The pressure has not changed, and it will not change tonight, or tomorrow, or for as long as the trench continues its own slow, patient work. The snailfish are still moving slowly across a seafloor no sunlight has ever once touched, and somewhere in the soft sediment beneath them, an amphipod is very likely feeding, right now, on a fragment of marine snow that began its long, unhurried descent from the sunlit surface many weeks earlier. None of this depends, in any way, on whether anyone happens to be watching. What has changed, slowly and only within the last century and a half, is how much of it we have managed to see for ourselves. A single weighted rope, lowered almost by accident from the side of a survey ship in 1875, a cramped submersible carrying 2 careful, quiet men in 1960, an uncrewed vehicle lost to a storm decades later after quietly doing its work, a solitary dive in 2012, a more thorough, more precisely mapped survey in 2019, followed by quieter years of amphipod nets, baited cameras, and sonar passes that rarely make the news but slowly add to the same long, patient record. Each of these moments added only a small increment of certainty to a place otherwise defined mostly by its stubborn resistance to being fully known. And each one, in the very act of doing so, revealed just how much more there genuinely was left to ask. Somewhere in that long list also sits a quieter kind of lesson, one that has less to do with the trench itself, and more to do with the people who keep returning to it. Every engineer who has ever designed a hull for that depth has done so knowing that the ocean does not forgive a miscalculation, and every biologist who has pulled an unfamiliar amphipod up from the sediment has done so knowing that most of what lives down there has never been named, let alone understood. That is not a comfortable position for a scientist to work from, and it is, in its own quiet way, exactly why the trench continues to hold their attention so completely, decade after decade, dive after careful dive. There is something worth carrying away from that discomfort, rather than simply setting it aside once the last dive is logged and the last sample is catalogued. Most of what surrounds us in ordinary life has already been measured, mapped, and explained many times over, until the explaining starts to feel like a formality rather than a discovery. The trench offers a rare, quiet exception to that feeling, a genuine reminder that even on a planet as thoroughly studied as this one, entire habitats can still sit largely unexamined, simply because reaching them honestly, carefully, and safely has never been easy. That is not a frightening thought so much as a grounding one. It suggests that curiosity has not run out of places left to go. Even here, even now, even after a century and a half of trying, somewhere above all of this, right now, a ship may be crossing that same stretch of the Western Pacific, its crew unaware, or only distantly aware, of the 11 kilometers of water and the tens of millions of years of slow geology sitting directly beneath their hull. That quiet indifference, the surface world, simply going about its ordinary business above a place this strange, is not a failure of attention. It is closer to the truth of how the whole planet actually works, most of it operating far beyond the reach of daily notice, continuing regardless of who happens to be watching from above. That is, in the end, closer to the real truth of the trench than any single fact about its depth, or its pressure, or its strange, patient biology. It is not a place that has been solved, and it was never going to be solved by a handful of careful visits spread across 60 years. It is a place that has been visited, briefly and rarely, by a species that spends nearly its entire existence within a few hundred meters of the ocean's surface, looking down into a stretch of water that has been quietly doing its own slow, deliberate work. Earthquake by earthquake, falling particle by falling particle, for tens of millions of years before we ever arrived to ask about it. The trench does not need us to understand it, and it never has. It has simply continued, the way it always has, patiently, in the dark, whether we are watching or not.